So I can go on changing this delay and find the values of h at different values of tau and get the total impulse response. So it's a very nice way of finding the impulse response of the system. So in experimentation, if you want to do this for a given for a unknown linear time invariant system, you need to have this white stationary white noise. Where do we get it? What do you generate it? Ideal white noise, ideal white stationary noise we can generate because natural processes have this property, but unfortunately I cannot do that because I need some amount of time correlation to do these integrations and all this. And any noise which is white by very definition has no correlation if there is a small amount of shift, right? Because remember what I have written here. Where did I write? I wrote somewhere. Here. What does this mean? This means if you shift the function x of t by even a small amount of tau, there is absolutely no correlation between that function and the shifted function. They have only complete correlation when they are exactly at the same time, but if one is shifted by small amount, then there is no correlation. So when we start doing this operation here, there should be no delays anywhere other than the fixed delay. You have problems of this nature, so you can't use natural noises because no time correlations. So we need to generate in laboratory a time function, a deterministic time function whose time correlations are well preserved, such that the correlation function of this x of t is like a white noise correlation function. That we are looking for a deterministic function whose correlation is like a white noise correlation. That means white noise correlation impulsive, right? That is what we wrote there. So it must be closely resemble an impulse. What kind of signals have this property? You remember pseudo noise sequences which we talked about in 102? PN sequences, which are generated by putting a shift register with a feedback, and the output that is a binary signal with a random zero crossings, and such signals have correlation function which is almost similar to this. There are other signals also, but most commonly used signal is a PN sequence. Are you with me or not? If you don't, not I'll repeat it. Remember in 103, 102 we said that if you have a shift register and then take the output and feedback, this output here is a periodic sequence, and this periodic sequence length is equal to 2 to the power of n minus 1, where n is the number of stages of the shift register, and depending upon what feedback connection you have here, you get a periodic signal, binary periodic signal of 2 to the power of n minus 1 length, which is either 1 or a 0, but the crossing from change from 1 to 0 will be random changes. Not random, deterministic, but almost resembling a random variation. And this function what you get here as a correlation function, which is approximately same as the correlation function that we are looking for. So people use a deterministic function, which is a function which approximates a random white noise by using the PN sequences, and test this system by using that signal here and delay it by some amount of tau, fixed value of tau, and evaluate it integral here and get the value of tau. Change this, get different value, change this. So you can scan the whole H of t. So it's a very beautiful way of doing it. The advantage of this scheme is that even if this system is fed with some other signal, that can go on. To this you add this signal, which is the PN sequence, and since this and that are uncorrelated, the system is not going to be affected by a small amount of this additional noise overriding the actual controls input signal. So you can do simultaneously whatever you are doing for the black box as input, and also simultaneously measure the impulse response of the system by using this PN sequence. People have used this technique. I understand the nuclear reactors are continuously monitored by using this method by applying a pseudo noise sequence here. So it's a very powerful method of finding the impulse response of the system dynamically while this system is running. You don't even have to make the system off to make this measurement. Okay. No question? Good. This gives a very interesting viewpoint to see if I am asked to find out a y of t with a given spectral density, converse problem. I want to generate a Whiteson stationary random process which has a given spectral density, then what do you do? Answer is very simple. You apply Whiteson stationary white noise here to a system with a transfer function Hj omega such that Hj omega square is equal to Syy omega. This is known. So, is there a way of extracting from this the Hg omega? That is the problem. If you know how to extract from this given spectral density the Hj omega, which is related by this, then I can put that transfer function here and drive it with a Whiteson stationary white noise, then I get a y of t which has this required power spectral density. So, this is a nice way of generating random processes for a particular requirement of power spectral densities. The question, biggest problem now is how do we go from here to here? It is very easy to go from here to here. Given this, I find the modular square, so I know this. But given this, how do I go backwards? This problem is what is known as this spectral factorization. Let us say the transfer function is h of s, right? Make s is equal to j omega. So, this will become hj omega, and hj omega mod square is equal to this into this. Why? Because h minus j omega is nothing but h star j omega. So, this product is nothing but hj omega square. So, hj minus j omega is nothing but hf minus s with s is equal to j omega.